I'm Dr. Ken Shepke, and today we're going to be speaking about COVID-19 vaccinations, and I'll be giving you an update on the current state in the United States with the various vaccine candidates, hopefully to give you enough information so you can stay informed yourself and make an informed decision on whether you might be interested in getting one of these vaccines, assuming they ultimately become available. So one of the things I see, and one of the concerns, frankly, is how do we get a vaccine so quickly? And does that mean that science cut some corners and we can't really rely on these vaccines? And really, I'm going to give you information on it, but I don't think that that's the case. I think it's just natural, advancement in science. So like I said, the smallpox vaccine took literally thousands of years for us to get our first vaccine. And then the next major advances took hundreds of years. And even the measles vaccine, to get a live attenuated vaccine, took them 10 years to get the strain of measles weakened virus that we can use for a vaccine. And then the Human Genome Project really created an opportunity for us to make some major advances and technological leaps in vaccine therapy. I'm going to go over why that particular project, while it doesn't really sound like it's related to vaccination, why it actually is very much related to how we can make vaccines so quickly. So if you remember, the Human Genome Project was a major thing a couple of decades ago, cost $3 billion. Over 200 labs in the United States plus 18 other countries collaborated in the effort to decode the human genome. It took 13 years to decode the human genome from 1990 to 2003. That's how long it took. So it was a major undertaking, took a long time. And because of that effort, it really advanced our understanding of genetic decoding. And nowadays, you can decode the entire human genome in 24 hours for less than $1,000. So that's the major leaps and bounds that have occurred based on that technology being advanced to this point. And the reason why that's important in terms of vaccinations is because of this. If you look at the genetic material in a human, it's roughly 6 billion bases in a human genome. Compare that to a fruit fly, which is only 123 million bases, or even to a bacteria like E. coli, that's 5 million bases. And then compare it to the COVID virus. The SARS-CoV-2 is the name of the virus that causes COVID-19. That's only 30,000 bases. So literally, it's not even a drop in the bucket compared to the human genome. So as you can imagine, we can figure out the entire genetic sequence of the virus really, really quickly. And that's why we were able to develop this messenger RNA vaccine so quickly. So messenger RNA vaccines is not a virus. That's one of the key pieces. Messenger RNA is basically a piece of genetic material that is a recipe to produce a protein. And your body does this every single day. It makes all sorts of proteins, but your body also has an immune system that recognizes foreign proteins that should not be existing in our body. So one of the ideas behind messenger RNA is that you use this recipe to create a protein, and you get that into a cell, make the cell make this protein, and then it activates your immune system. So the really cool thing about these messenger RNA vaccines is that you can use this to create any protein that you want. And one of the things that we're using that researchers are using this for is even to develop therapy for cancer. Because in addition to creating vaccines and create proteins for infectious diseases, when you look at cancer, a lot of times cancer cells, they create mutated proteins. So in addition to being mutated cells, they begin to create proteins that are not normally seen in your body. So if you can get the genetic material or the recipe, so to speak, for that mutated protein and put it in one of these lipid nanoparticles, then you can inject it and develop an immune response and teach your immune system to kill any cells that are expressing that mutated protein. And in fact, we are seeing some improvements in therapy for melanoma using exactly this type of technology. So again, this is not, it's newer, but it's not brand new just for the pandemic. Researchers have been working on these type of vaccines for a while. Now, the nice thing about this is it's ultra rapid technology. I mean, you can really get this, you can get the genetic code for whatever you're trying to make really quickly, wrap it up into these nanoparticles and create it. In fact, in this instance, it took 62 days. That's it, 62 days, not thousands of years, not hundreds of years, not 10 years, 62 days from the moment of deciphering the genetic code of the SARS-CoV-2 virus. Again, that's the virus that causes COVID-19. From that point to developing a messenger RNA lipid nanoparticle vaccine and injecting it to the first human. So now you wonder, if we had a vaccine within 62 days, why are we not using it right now? And that's where the next piece of vaccine development comes along, which is all the safety and efficacy studies. So the way these studies work is you give half your study population the vaccine, and you give half your study population a placebo that you would expect not to develop any sort of immune response. But then you have to wait some time, and as those people go about their daily lives, some of them are going to come in contact with the infection that you're trying to protect them from. And then after you've had a certain number of people in your study get infected, then you look at it and you say, all right, of the people that developed the infection, how many got the placebo and how many got the vaccine? And you compare those two groups and you can say, oh, well, look, the folks that got the placebo, lots of them got the disease, but the ones that got the vaccine, not too many got them. That's how you calculate your efficacy ratio. Now, one of the reasons why you don't just take the messenger RNA and inject it into the body straight like that is because messenger RNA is a very fragile molecule. And your body has all these enzymes that break down the messenger RNA and it'll just destroy it immediately. So that's where the technology to protect the messenger RNA by putting it inside these lipid nanoparticles came from. Now, the lipid nanoparticle is basically a little tiny ball of fat. And the messenger RNA gets inside that, and that protects it from the enzymes. And the important thing is when you inject that, the lining of your cell also has lipids on it. So those two lipid layers then come together and allows the messenger RNA to enter your cell. Once it's inside your cell, then that messenger RNA comes out, and then the cell's normal machinery in the cytoplasm, or the liquid part of the cell, takes over and takes that messenger RNA and starts creating the protein. In this case, it creates the spike protein. Now, the spike protein on the COVID virus is basically the attachment molecule. That's where the virus, that's the protein the virus uses to attach to our cells. And once it attaches to our cells, it gets inside the cell, and that's how it gets to replicate itself. So making that spike protein is an important step because we want our immune system to recognize that so that antibodies can be developed against that. And I want to talk about that in a moment. So let's talk about the two main messenger RNA vaccines that are very soon. In fact, Pfizer, I think, just filed for emergency use authorization with the FDA. Moderna is just going to be literally just behind it by a matter of weeks. Let's talk about the technology behind these two. So first, again, this is a messenger RNA vaccine. It is not a virus. It does, however, have to be stored. Again, the messenger RNA is a very fragile molecule, and it has to be stored at a very ultra cold rate. So in this case, negative 80 degrees Celsius, if you want to store this vaccine for long term. So in this case, for 6 months, if you want to store it for 6 months, you have to put it down to this ultra cold temperature. Now, a normal freezer does not do this. So you do need a special ultra cold freezer to get down to that cold. However, you could put the vaccine in a regular refrigerator, and then it's good for 5 days. Not a lot of time, but that should be plenty of time if you have an efficient vaccination scheduling system so that you can use up the vaccine before it goes stale. Once you take the vaccine to room temperature, now you've only got about 6 hours to use it up before it goes bad. Now, in the Pfizer study, they had 44,000 participants. They had a good diverse background, which is fantastic. They had zero safety concerns, a 95% efficacy rate, which is fantastic, and very importantly, both antibody and T-cell immunity. I want to talk about that just for a moment here. So if you look at your immune system, you can think of it like a military, right? And the military has different branches. So you have like the Army, your ground forces, that would be like your antibodies. And then you have like your Air Force, and that's like your T-cells. So basically what the antibodies are, they're like these proteins that your immune system make that go out and they attach to the spike protein and basically cover them all up. And if you cover up all the virus's spike proteins, then the virus doesn't have any attachment point where it can attach to the cell. So now it can't get into your cell because you've covered up all the spike proteins with antibodies. That's one part of your immune system. The other part of the immune system is the T cell part of the immune system. And it's a little harder to measure T cell immunity. Antibody testing is pretty simple. T cell immunity is a little more complex in the lab to figure out whether you have T cell immunity. But what the T cells do is they basically recognize cells that have been infected with the target antigen, in this case, the spike protein. And then what happens in a normal infection is the virus gets into your healthy cell and starts reproducing itself. And in the process of reproducing itself, they start having all these spike proteins on the outside of the cell. The T cell then recognizes those spike proteins on the outside of what used to be a healthy cell, is now an infected cell, and realizes, hey, this cell has been taken over. It's now an infected cell, and it can kill that cell. In addition, the T cell also gets the cells that produce antibodies to ramp up their production. So the T cell is really important in viral infections like this, where you get the infection inside your cell. So we really want to see that antibody and T cell immunity for this particular disease. Now, the nice thing is that we are nearing the end of this process here, where we may get emergency use authorization sometime in December, and Pfizer, BioNTech, that collaboration thinks they may be able to deliver somewhere between 20 and 30 million doses, provided things go through and they get emergency use authorization by the end of the year, maybe able to get 20 or 30 million doses out to us. Pfizer, because they have to ship it in ultra cold, they've developed their own dry ice shipping container, and you can actually store the vaccines in this sort of container. That's basically dry ice you're seeing there in that picture. As long as you continue to top off the dry ice, you can keep it in a container like this at the required ultra cold temperature for up to 15 days. Now, Moderna, very similar technology, not identical, but very similar, also a messenger RNA vaccines, also not a virus. Their stability, I guess, is a little bit different. You can actually put this at a regular freezer level. So not the ultra cold freezer, just but like a regular freezer temperature. You can store this at 6 months, so it's a little bit more stable, which is nice. You can put it in a regular refrigerator. So at refrigerator, but non-freezer temperatures now, just the regular refrigerator temperature for 7 days, and perhaps even as long as 30 days. Moderna did say on one of their webinars that they've got data that shows stability out to 30 days, but they're not officially saying that yet because they need the FDA to give them the thumbs up on their data on that. This, same like Pfizer, once it's open, you got 6 hours at room temperature to use it up. They also had a big study, 30,000 participants, also diverse background. Zero safety concerns in this one, also in their study so far, and greater than 94%. In fact, it was 94.5% effective. Also, both antibody and T cell immunity, which is fantastic. And they also think they can get, assuming the process goes through and the FDA gives them a thumbs up on their emergency use authorization, they may be able to do up to 20 million doses available before the end of 2020. Now, I do want to go over this efficacy thing, just a little more depth. It's the fact that they have 94, 95% efficacy in their studies. This is a grand slam. And the reason why I say that is because some of our best vaccines in history, like the measles, for example, has high 90% efficacy rates. But if you look at some of our more routine vaccines, like the influenza shot that many of us get every single year, that averages about 40%, 40% efficacy. So to get something that is like literally on par with some of the best vaccines we've ever had, it's a grand slam. It's great news for the world for this pandemic. Now, vaccine supplies are going to be included with shipments of these vaccines. So it'll be coming with the needles, the syringes. It might not have enough PPE supplies, particularly gloves, as I was reading into this. So if you're going to be delivering vaccines, you might want to make sure you got enough PPE, particularly the gloves. I want to talk a little bit about AstraZeneca and some of the other three that are in the pipeline for the United States into phase 3 trials. AstraZeneca is using a chimpanzee adenovirus. This is a benign virus that causes a cold in chimpanzees that they've genetically modified so they cannot reproduce itself. And they've added the genetic material that makes the COVID-19 spike protein to that. So when you get injected with this, this is older technology. It's kind of something that's been done in the past for vaccines. Takes a little bit longer, which is why they're not as far along as the newer messenger RNA technology. But they're up there. I mean, they're getting pretty close to finishing their phase 3 trial as well. The good news from AstraZeneca is their early results show both an antibody and T cell immune response at high levels as well, and they think they'll be ready to apply for emergency use authorization in early 2021. The Johnson & Johnson vaccine is similar to AstraZeneca. It's also an adenovirus that has been made weak, that's unable to replicate, that they added the genetic code to it for the spike protein for COVID. Also showing good T cell and antibody response. The important thing about Johnson & Johnson vaccine is this is a one-shot vaccine. All of the others that we're looking at so far the plan is to have 2 shots where you get your first shot and then you get a booster shot In the case of Pfizer, Moderna, that's anywhere from 3 to 4 weeks between for those two companies' vaccine candidates. So you'll have to get the same shot twice for all of those. But the Johnson & Johnson, they're shooting to have a single shot, one shot, and you're done. You won't have to come back for a repeat shot. So that's one of the nice things about Johnson & Johnson. So I hope I've informed you and given you a lot of information, and gotten you a little more up to date on the vaccines that are fortunately coming. That's right around the corner now, which is great news. And I wish you all good health and continue to stay safe. And thank you very much for watching.